It's my great pleasure to moderate this very interesting topic at the moment on the formal verification side, formal reasoning, and we have basically three panelists. I will just go through a short round of introduction of each of them, and then we just start with question answering. So we have on board Professor Jeannette Wing. So Jeannette is Director of Data Science Institute and Professor of Computer Science at Columbia University. From 2013 to 2017, she was a Corporate Vice President of Microsoft Research. She is Adjunct Professor of Computer Science at Carnegie Mellon University, where she twice served as the head of the computer science department and had been on the faculty since 1985. From 2007 to 2010, she was the Assistant Director of the Computer and Information Science and Engineering Directorate at the National Science Foundation. She received her SB, SM, and PhD degree in computer science, all from MIT, Massachusetts Institute of Technology. Jeannette General's research interests are in the area of trustworthy computing, specification and verification, concurrent and distributed systems, program languages, and software engineering. Her current interests are in the foundation of security and privacy with a new focus on trustworthy AI. She was or is on the editorial board of 12 journals, including the Journal of the ACM and Communication of the ACM. Jeannette is known for her work on linear reusability, behavioral subtyping, attack graphs, and privacy compliance checkers. Her 2006 seminal essay titled Computational Thinking is credited with helping to establish the centrality of computer science to problem solving in fields where previously it has not been embraced. She is currently a member of American Academy of Arts and Science Council, the board of the trustee for Institute of Pure and Applied Math, the advisory board for the Association for Women in Mathematics, and the Alibaba Damod Technical Advisory Board. She has been chair and or a member of many other academic, government, and industrial advisory boards. She received the CRA Distinguished Service Award in 2011 and the ACM Distinguished Service Award in 2014. She's a fellow of the American Academy of Arts and Sciences, American Associate for Advancement of Science, the Association of Computing Machinery, ACM, and the Institute of Electrical and Electronic Engineers. We have Changliu Liu. Changliu, if I'm not misspelling her name, her first name is an assistant. Is an assistant professor in Robotics Institute at Carnegie Mellon University. Her research interests lie in the design and verification of intelligent systems with applications to transportation and manufacturing. She published a book, Designing Robot Behavior in Human-Robot Interactions, with CRC Press in 2019. She is the recipient of the 2019 Amazon Research Award. And finally, we have Huan Zhang. Huan is currently working as a postdoc researcher at Carnegie Mellon University with Professor Ziku Kolter. He received his PhD degree in 2020 at UCLA with Professor Cho Yu Hsieh. And received his Master of Science degree in Computer Engineering at UC Davis in 2014. Huan's research focuses on the robustness and trustworthiness of artificial intelligence, especially on using provable methods to evaluate and enhance the robustness of machine learning models, such as deep neural networks and tree ensembles. Huan developed Cron, one of the earliest efficient neural network verification algorithms based on linear relaxation of neural networks. Huang systematically studied the robustness of many machine learning scenarios, including reinforcement learning, natural language processing, and image generation. And he has co-authored over 40 papers in leading machine learning and AI venues. Huang was awarded an IBM PhD fellowship during 2018 to 2020. I'm very pleased to have you on board and looking forward to a very interesting discussion altogether.
So with respect to scalability, obviously AI systems really challenge current verification techniques beyond what we know can be done because of the large state space, if you will. I'm still hopeful that there are certain methods like counterexample, guided abstraction and refinement, and technologies that are coming to fore, like interval analysis and so on, that can help with the scalability issue. Scalability has always been with us in formal methods, and we've always tackled scale, kind of making incremental progress, but usually with huge successes. Whether it be what we do with a model, like abstraction, or what we are able to do with approximate, maybe not complete techniques. SMT solvers have really helped scale up formal methods, for instance, and we've been really exercising SMT for decades. So I'm hopeful that the verification community, if they put their heads together, can start thinking about methods and scalability issues. I'm more daunted by the problem I raised in the earlier session, which is, has one formally specify in any meaningful way the environment or the data distributions? But here again, I see it as a verification challenge to the community.
I have some comments.
Sure, please.
So like for me, actually, before I started working on machine learning, my background was on computer engineering and computer systems. So for me, like I think one of the most important things is we need to make sure we can utilize the modern machine learning accelerators such as GPUs and TPUs for those verification problems. Because if we just rely on CPUs, it can just be too slow. So one trend is trying to develop algorithms that are actually parallelizable on those machine learning accelerators. And for verifiers, I think it's actually a challenging problem because if you use like mixed integer linear programming, SMT, or even linear programming, it's very hard to utilize those machine learning hardware because the solvers are only compatible with CPUs, and there's a reason because these algorithms are fairly complicated and they cannot be fit into the computation model of GPUs. I think one reason modern deep learning can succeed is that the use of large data and also the use of machine learning accelerators like GPU and TPUs, and without those we cannot really succeed. And I hope that there are like more methods that can compatible with those machine learning accelerators for verification. And one of our works, the AutoLeaper library I just introduced, this was actually one step towards that direction, and I hope there can be many other methods that improving our results. Thank you.
Yeah, I would also like to add some perspective from the application side. So a lot of our work is trying to apply those verification techniques to solve the real-world robotic problems. And we do see a huge gap between what is doable with the current formal methods and what we need in robotics. I think there's still a lot to do in terms of scale current methods up. And one of the approach we're currently doing is just to compose different things together, like doing a kind of more higher level optimization. I can see that will be a viable approach to make sure that we can apply existing methods.
Let me speak to this. Let me start, and Changliu and Huan can add their thoughts, because I've been thinking about what is the difference between proving some property like for all x p of x, where x is the input variable to some program or some model, and p is a property we want. So first of all, there is definitely a challenge of specifying formally what the property is, but I do think some of these properties are formalizable. So robustness there may be many definitions of robustness, but we can choose one. And we already know there are many definitions of fairness, and we can choose one. I also think that what we'll probably be looking out for are trade-offs between these properties anyway. I think the real challenge is the for all x p of x. I think we all know that we probably can't say for all. So what can we say? I think what we can try to do is to say for all input distributions in a class of data distributions. And so, yes, that means we are not doing a for all X proof, which is what we would like to be able to do, but at least we are formalizing what that class of distributions is. And I think a lot of the work in robustness is really trying to grow that class of distributions so that a particular machine learning model is actually robust within that class of distributions. And so if we can formalize that, then we have a chance of doing some kind of verification that's with respect to a larger set of input distributions than just one,
yeah,
which is what we are doing today. So that is the hope. And I'm just posing that as a way to think about it. And that's not even addressing what logical frameworks do we need to do the verification. And I was not talking about a system level verification, where I know there's been some excellent work in system level verification for exactly the kind of self-driving car application you're talking about. Verif AI, the work that by Sanjeev Seshia out of Berkeley, addresses that very problem, where they're using simulation. So I'm not saying verification is the be and end all. For system level verification, there may, and even at the machine learning model verification, my guess is that we're going to have to make progress, start integrating these techniques.
So I would like to make a distinction between like perception problems and control problems. I think the major difficulty in the sense that CPS is very difficult to verify as a whole is that we don't have a good model for the perception. If we want to say for all the curvature, road curvature, have some certain angle, it's very difficult for us to capture all the perceptual space for that condition. But if we can do that, the control problem, I think it's relatively easy to verify. We have a bunch of like the Lyapunov analysis and stuff. And I can see that in the verify, they are trying to get around this perception problem by introducing like low dimensional representations of the environment. But in order for us to fully verify those maybe image data driven kind of perception, we still need to do more work, and especially along the way that Jeannette just suggested. I would suggest we can think another way around, like think about a different dimension. And I would like to give one example that is a successful verification of those learning techniques in ensuring safety of industrial robots. So what they do is they first verify their sensor. Their sensor is not image-based. Their sensor is the kind of point cloud-based. And they verify their sensor, and then they get a very good specification of what the output the sensor can get given all different real-world situations. So then they overcome the perceptual problem that we discussed earlier. And then given the desired sensor range, they can do a control verification that their robot is always acting safely with respect to the environment.
Very good point. This is what we actually doing now at Audi.
Oh, really? Cool.
Yeah, but there is a big issue with that. Basically, what you're saying and what we are doing is assume guarantee-based reasoning. So basically, you verify the sensors, and based on the possible outputs of the sensors, you do the verification of the, as inputs to the perception system, you do the verification of the perception system, and so on. So basically, it avoids you to go through a black box verification that I'm strongly against of it, rather going through the components verification. That may work, definitely, but still, it cannot bypass the issue that we have for this perception system verification, because all the guarantees that you get on the verification of the perception part is bound to the preciseness of the results that you get on the verification of the sensor system. And imagine we are not working on it with a single sensor. We have multiple sensor system deployed in the car or airplane, and you do sensor fusion, and all results basically results on the output of the sensor fusion right after the sensor fusion component. So this is definitely a way to go, but I'm not really sure that we can bypass the issue of safety verification for the perception system in a very promising way that can be tied to the rest of the system for coming up with the sound guarantee, provable guarantee at the system level. But okay, so Jeannette, you are expert also in probabilistic programming. How can we leverage techniques from probabilistic programming in order to do an efficient verification of machine learning components?
I'm hardly an expert in probabilistic programming, but what I have been watching is a probabilistic programming community. And even at my time at Microsoft Research, there was some very interesting work in probabilistic programming from 2 points of view. One is from the traditional programming language point of view, where you're adding probabilistic constructs or the ability to draw the value of a variable from a distribution, and you can write that syntactically in the program itself, whether it's a C-like program or your favorite imperative programming language. And there were some very interesting applications trying to use those kinds of programs to do verification. Probably one of the most relevant is the work by Kapoor and Dorsa Singh. Dorsa is now at Stanford, and using probabilistic logics and probabilistic programming to actually prove something about control systems. I think they were using it for drones, and so it was robust real-time control systems, and proving some kind of property about, not through the vision system, saying it's not going to crash into a wall or something like that. So I think there's some hope along those lines, because once you have a program written in a programming language that presumably has some kind of formal semantics, then you have a different angle towards doing some kind of proof. The other camp in probabilistic programming, which I'm exploring with one of my students, I don't yet know how to incorporate in the formal verification and robust AI framework, but I think there's a possibility, and that is the STAN probabilistic programming language, which is very prevalently used in the statistics community and has many, many users in the science, the government, and non-computer science audiences typically. They are heavy users of STAN. STAN is open source. It is a way to build a model of your data distribution. So it is possibly a language in which one can use to specify D in my framework of DM satisfies P. I'm not really sure. I haven't done it. I don't know how to do it. But it seems that it's a starting point. Mm-hmm. So I do think more generally that in my double turnstile, which I use for standing for the logical framework in which one needs to do the verification, I do think we're going to need to lean on probabilistic logics, hybrid logics, that's I think this is again where AI systems really up the ante in terms of everything with respect to traditional computing systems and verifying them.